All right, so looking at question number 12 and 13 and the rest of them, we're trying to figure out the emission spectrum. We've got 1, 2, 3, 4 different colors. There's like red, violet, blue, and another yellow. And these colors are what we see in the spectroscope. And they all represent a specific wavelength. And beta, this is the Greek symbol beta, just looking at it, is apparently 486 nanometers is the wavelength of beta, 486. So I'm going to write that, 486 nanometers. And we're going to try to figure out ultimately what is the amount of energy that is in that wavelength. But before we do that, we're going to have to do two equations. Number 12, we're going to be using the equation that finds frequency, which is the speed of light equals wavelength times frequency. And where am I getting that equation? I'm getting it right from the first page. Speed of light equals wavelength times frequency versus the energy of the photon equals Planck's constant times v. So ultimately we'll have to do both of those equations, across number 12 and 13. So speed of light, anybody remember what the speed of light is, or see that on your sheet?
300,000 meters per second.
300,000 sounds about right. 3 times 10 to the, I think it's more, it's 1, 2, how many would that be? Now I'm curious.
Yeah, it says it's
1, 2, 3, 4, 5, 6, 7, 8.
No, it's 300 million.
300 million, you got it. So if you like 300 million, you can type that in.
It's
or
more 300,000 kilometers per second.
There you go. 300,000 kilometers versus 300 million miles. I'm going to do 3.0 times 10 to the 8th, but if you want to do 3 with 9 zeros after it, or 8 zeros, you can do that. All right, that's meters per second. And then wavelength, I would type in 486 nanometers, but I've got nanometers and then I've got meters. Is that a problem? Yes. We got to make sure that they're equivalent units. So I got to convert nanometers to meters. So I put meters on top, nanometers on the bottom. Now I could put 1 on the top, 1 on the bottom, it doesn't matter. If I give 1 to my bigger unit, that means my exponent is going to be positive. That's a little more convenient for me. And this would be a flashback to chemistry if you got the great mighty King Henry died by drinking chocolate milk, making Nancy pout. This acronym represents tera, giga, mega, and then the common ones, kilo, hecto, deca, base unit, deci, centi, milli, all these different metric prefixes. And then we go to micro, nano, pico. And remember, the main 6 are a difference of 1 step in terms of moving the decimal place, like 1, 2 steps moving the decimal place. But if you're going to the outer 3, they're going to be a difference of 3 steps. So we got to figure out, all right, going from base unit meter all the way to nanometer, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to write 1 times 10 to the 9th nanometers on the bottom.
Oh, well, I could do like twice as much though.
So these smaller ones going from milli to micro, it's a difference of 3 steps. They don't really have a prefix name for something that's 1 step over beyond milli. The next thing is just micro. It's because it's super small, but micro is significant because we have microscopes that can help us see the things that are super small. And then we have other technology that can help us find the even smaller nano. Whereas the middle 6, those are things we can see with our eyes. So we can be a little more specific. Just one move of the decimal spot. All right, so 486 times 1 divided by 1 times 10 to the 9th. This would be where you need a calculator. Otherwise, you can just go into Google Calculator, and that would work. Whatever's easiest for you. I got 486 divided by 1 second E. I always do the E button in the calculator, which stands for times 10, and then 9. That's giving me that very small number. I mean, you could put all those zeros, but I get a little lost in the zeros. So I'm going to convert that to scientific notation. I got 4.86. I got to make sure my whole number is between 1 and 10. And I'm moving 1, 2, 3, 4, 5, 6, 7. All right. So if my number is a decimal number, is my exponent negative or positive? Negative. You guys got it. Nice. Nice thing about earth science is, in theory, you took all the base classes, and now you can take all that knowledge and apply it to actual stuff. All right, this is meters. So all we did right here is we're converting nanometers to meters. Now that you know the conversion factor, you can just kind of make a note of that, and for future problems, kind of go back and just use that instead of having to do the King Henry each time. All right, so our wavelength is 4.86 times 10 to the negative 7th meters times frequency. All right, besides the scientific notation, this is looking a little more familiar where we have a single variable and we can isolate. So what would be the last step to this problem? Nick's got it. What's the last step to this algebra? We divide both sides by? Oh, that's right. That's right. All right. You know what class we're in? Okay. It's okay. Anyone else want to share the last step? What do we do? Divide both sides by... Do we divide them both sides by V or by 4.86?
Wait, so hold on. Is capital V and lowercase v pretty much the same thing?
They're the same. Yeah, technically it's going to be lowercase v.
Because it says capital V equals frequency of S powered by -1, and then lowercase v is the frequency in S powered by -1. Is it pretty much the same thing?
They're the same thing, yeah. That's kind of, that's a little goofy. Yeah, we're saying we got capital V with lowercase v, but they really should be the same. So, it was probably when it got converted from PDF. It was all messed up. Alright, so, what I'm going to do is I'm going to divide both sides by the 4.86 times 10 to the negative 7 meters. So essentially what I'm doing is I'm taking 3.0 times 10 to the 8th meters per second and dividing it by 4.86 times 10 to the negative 7 meters. And that's going to get me my frequency. And typically my frequency is always to a power of 14 when we're doing the Balmer series. All right, there we go. 6.17 is my frequency times 10 to the 14th. And it can be either written as hertz or 1 over a second, whatever you're liking. Questions on that? Basically, that's how many wavelengths are happening in a second. That's what that's saying. That's a lot of wavelengths because it's super, super tiny. Yeah, if you want to do it on paper, go for it on paper. It would drive me nuts doing it on a computer. So then you got to do superscripts, all that. It drove me nuts because I had to make this on the Google Doc.
Yeah, well, if you have the international U.S. keyboard on, that makes a lot.
That would help.
Yeah, the U.S. international keyboard makes superscripts kind of easy.
Moving on to number 13, it says use Planck's constant to calculate the energy of the same line we were looking at from the hydrogen emission spectrum. So we want to find energy, and the equation for energy is the particle model. Energy of photon equals hv, Planck's constant times frequency. So I'm going to rewrite that. Energy equals Planck's constant times frequency. All right. Planck's constant is always the same value. It is 6.626 times 10 to the negative 34 joules times seconds. So we got 6.626 times 10 to the negative 34 joules per second. That's my H, Planck's constant. My frequency, V, is what I found in the previous question.
Oh, so that's equal to H and not E. Oh, you're just building onto it.
Yep. So H times V is equal to my energy, and my V is 6.17 times 10 to the 14th hertz, also known as 1 over second. I'm leaving in the 1 over second so that you can see how my seconds actually will cancel out, and I'm left with joules, and joules is the unit for energy. So then I'm going to have to take my 6.17 times 10 to the 14th, times it by 6.626 e negative 34, and I'm getting 4.1 times 10 to the negative 19. 4.1. So what I just found here was the amount of energy that's released when an excited electron goes down to its ground state, forming, in this color, 486 is closer to the ultraviolet, so it's a violet purple color. That purple color is a result of the transition or release of this amount of energy, 4.1 times 10 to the negative 19. Itty bitty bitty amount. Questions so far? Alright, so there's 3 of these. We're going to do the second one together. But I'm going to have you guys kind of walk me through this. We got, this time, the gamma line. And the gamma line is 434 nanometers. 434 nanometers. Okay, I want to find the frequency. I have wavelength. Which equation do I use?
6.17.
Well, that's for to find the energy. So I'm kind of doing something up here. Up here, when I was looking for frequency, I used speed of light equals wavelength times frequency. So I'm going to use that one again. And my speed of light, here I said it was 3 times 10 to the 8th. Just confirm speed of light, 3 times 10 to the 8th.
Wait, so how'd you get 434 nanometers?
434 is at the very beginning of the page, or if you scroll to the top, we got the 4 wavelengths for delta, gamma, beta, and alpha. 434. Yep. Otherwise, yeah, we wouldn't be able to do the problem. 434 is another violet hue. So my speed of light, again, is 3 times 10 to the 8th. My wavelength is 434, but that's in nanometers. I got to convert it to meters. What's my conversion factor that I want to use? Meters is on top, nanometers on the bottom. How many nanometers are in a meter? Bigger than that. You got it. 1 times 10 to the 9th. Let's not make this harder for us than it already is. We already did the work in question 12. So let's just reuse that. And this is going to, when you plug in your calculator, it's going to be 4.34 times 10 to the negative 7th. And that's meters. So I'm going to type that in, 4.34 times 10 to the negative 7th meters. I'm going to times that by frequency. And what's the last step to solve this? Divide. You got it. So I'm going to divide by 4.34 times 10 to the negative 7th. 4.34 times 10 to the negative 7th. Alright, so 3e to the 8th divided by 4.34 e to the negative 7th. Looks like it's 6.9 times 10 to the 14. I'm going to just say 1 over second, also known as hertz. Alright, there we go. So basically, we got this huge number of wavelengths that are kind of traveling in 1 second. A lot of wavelengths. All right, doing this last one together. We got gamma line still. We want to find the energy. We know energy equals Planck's constant times frequency. So I'm going to use the other equation. Energy equals Planck's constant times frequency. Anybody know what Planck's constant is? 6.626 times 10 to the negative 34. Joules times second. And in my frequency, what am I going to put for frequency? It's the same wavelength we were talking about in number 14. We found the frequency to be 6.9 times 10 to the 14th. So we're going to put 6.9 times 10 to the 14th, 1 over second. When you multiply those two values out, you get your energy. And I'm getting, for my energy, 4.58 times 10 to the negative 19 joules. That's how much energy is released when I have the purple-violet line. All right, your job is to work on 16 and 17. I'll give you a hint. It's just like 12 and 13 and 14 and 15. Same thing. The only difference is we're dealing with delta, which is 410. So now we're dealing with 410 nanometers as our wavelength. So you guys can try the rest. All right, guys, walking through this one, we want to find the frequency. We have wavelength, and then we also have speed of light. So C equals wavelength times frequency is the equation we're going to use. What's the speed of light? Anybody know?
We know times 10 to the 8th meters per second.
You got it. 3.0 times 10 to the 8th meters per second. This equals our wavelength times frequency, but our wavelength it's in nanometers, and we want it to be in meters. So what do we convert it to? Like, what's our conversion factor? How many nanometers are in a meter? Anybody know? You got it. 1 times 10 to the 9th. So when we take 410 times 1 divided by 1 times 10 to the 9th, we're going to get 4.1 times 10 to the negative 7th meters. That's our wavelength times our frequency. Last step is divide both sides by 4.1 times 10 to the negative 7th. And we should get, what was it, 7.3?
7.317.
Times 10 to the 14th hertz, or 1 over seconds. All right. That takes us to number 17. We're looking for energy. So we're going to use the other equation, which is energy of a photon equals Planck's constant times frequency. Taking a step back, the frequency, this is how many waves are pass in 1 second, which is a super large amount. So energy equals 6.636 times 10 to the negative 34th joules per second. That's our Planck's constant. And we times it by our frequency from the previous problem. And what was it? 4.848 times 10 to the negative 19 joules. And there you have it. Quantum mechanics.
So Mr.